So, let's go. You want proof. You want the saucer on the lawn. You want the radio signal that says hello in a language nobody on Earth speaks. You want it loud, you want it photographed, and you want it on a Tuesday morning so it ruins your boss's coffee. That's not how this works. The strongest evidence for alien life looks nothing like a UFO video. It looks like a chemistry report, a spectrum, a graph with error bars, 8 quiet discoveries, all of them peer-reviewed, all of them sitting on the desks of people who get nervous when they say the word alien out loud. None of them, by themselves, is a smoking gun. Together they're a chorus. And the song they're singing is the same one, over and over in different keys. That you are not as special as you think you are. That the universe is set up to make life. That it might have already. That it might be making it right now in places we can already see with chemistry we already understand. 8 discoveries. None of them about little green men. All of them about the quiet, steady accumulation of evidence that says, the silence is the strange part, not the noise. Number 1. Bennu's chemistry already had life's alphabet on it. In September of 2023, a capsule fell out of the sky over the Utah desert. Inside, it was about 200 grams of black powder, scraped off the surface of an asteroid called Bennu. The asteroid is older than Earth. It has been drifting through cold space for 4.5 billion years, never touched by anything alive. NASA opened the capsule in a clean room. They put the powder under instruments most labs will never see. And what they found in it should have changed the news cycle for a week. 14. Of the 20 amino acids life on Earth uses to build every protein in your body, 14 were already there. Sitting in a rock, assembled by chemistry, in deep space, with no biology anywhere near it. Then they found the nucleobases, all 5 of them. Guanine, adenine, cytosine, thymine, uracil, every letter in the genetic alphabet, every base that makes DNA, and every base that makes RNA, in a rock. Then they found ribose. Ribose is the sugar that holds RNA together, the same sugar your body is using right now to read a gene and make a protein. There it was, in the asteroid sample, already made. Then they found the salt. The Bennu sample has sodium-rich salts in it, salts that only form when liquid water evaporates from a brine. Bennu's parent body, the bigger asteroid that broke apart to make Bennu, had its own ocean once. A small, briny, warm pond with the building blocks of life dissolved in it, drying out under a black sky. Read that again. A rock floating in space had its own ocean. And in that ocean, the chemistry of life was running. Not metabolism, not reproduction, not yet, but the parts were there. The atoms had already arranged themselves into the right shapes. And here's the part that breaks people. The amino acids on Bennu are racemic. That means they come in both left-handed and right-handed forms in equal amounts. Life on Earth only uses left-handed amino acids. So when you find a mixture, this isn't contamination from a glove or a fingerprint or a sneeze in the clean room. This is the real thing. Made out there. Brought down here. There's even a 6th nucleobase hint. A faint trace of tryptophan, an amino acid that has never, in the entire history of meteorite chemistry, been detected in space before. The team called it tentative. They didn't want to publish it without more samples. But if it holds, there's a 15th letter in the alphabet and it just showed up on a rock. Bennu isn't the first asteroid to do this. It's not even the second. But it's the cleanest, the most pristine, the least contaminated. And it's the loudest statement yet that the recipe for life isn't built on planets. It's built in space. The kitchen is out there. Earth just got lucky enough to set the table. So here's the first question to sit with. If the ingredients are already prepared, in cold, dark places, in basically every rock that's ever been carefully studied, what stops the rest of the recipe from happening somewhere else? Nothing. There's still chemistry to do. There's still time to wait. There are still planets to land on. But the hardest part, the part nobody could explain for a century, that part is solved. The pantry is full. Number 2, a star that keeps blinking wrong. There's a star about 1,470 light years from here. Its catalog name is KR 8462852. Its common name is Tabby's star, after the astronomer Tabby Boyajian, who first realized something was off. For a few years, Kepler, the planet-hunting telescope, stared at this star, and what it saw didn't match anything anyone had seen before. Stars don't normally dim much. When a planet passes in front of one, the brightness drops by maybe 1%. A really big planet might block 2%. A swarm of comets, if they happen to line up perfectly, might do something weird for a few hours. Tabby's star dropped 22%, 22%, in days, in patterns that didn't match anything orbital, no clean period, no tidy curve, just deep, irregular, asymmetric dips that should not happen. The first explanation was instrument error. They checked. It wasn't. The second was a giant cloud of dust. That was the favorite, and it still mostly is. Dust blocks shorter wavelengths more than longer ones, and Tabby's dimming does behave a little like that, almost like dust. But here's where it stops being clean. A swarm of dust big enough to block 22% of a star's light should glow. Specifically, it should glow in infrared because the dust would be heated by the starlight. Astronomers looked for that infrared signature. They didn't find one. There's no warm dust disk where there should be a warm dust disk. Then somebody dug into archival photographic plates, actual glass plates with chemical emulsion from the 1890s, and tracked the star's brightness over a century. Between 1890 and 1989, Tabby's star had also faded by about 14%, slowly, steadily, over 100 years. So now you've got two problems: the short, deep, irregular dips, and the slow, decades-long fade. No dust model explains both at once. Other ideas came in. A planet that just got pulverized by a collision. A swarm of fragmented comets. A strange object passing through the system. None of them quite worked. Every paper said the same thing in the discussion section. Our model fits some of the observations. Not all of them. Some. And then, in 2015, an astronomer at Penn State named Jason Wright said the quiet part out loud. If you wanted to build a model that fit all of the data, the depth, the irregularity, the long fade, the wavelength behavior, the missing infrared excess, the cleanest fit was something built. Something engineered. A partially constructed megastructure, a Dyson swarm in early stages, harvesting the star's light, casting irregular shadows as it grew. He wasn't claiming it. He was saying it fit. The mainstream view since has drifted back toward dust. Dust does the most of the work. Most astronomers asked today will tell you it's probably dust, but probably is doing a lot in that sentence because no dust model fits everything. And here's the part that stays with you. There are more than 4,000 stars now confirmed to have planets. There are a few dozen with weird transit signatures. Some of those have been explained, some haven't. Tabby's star is the loudest of them, and nobody has closed the case. The viewer wants a verdict, there isn't one. There's just a star that keeps blinking wrong, in a way that nothing we know about can fully explain. That's not proof, but it's a hell of a question. Number 3. A moon spitting samples of its ocean into space. Jupiter has a moon called Europa. It's a little smaller than ours, it's covered in ice. The ice is cracked into long, dark, rust-colored lines that look like fault lines in cold glass. Underneath that ice, and this part is not in doubt, there is an ocean. Not a pond. Not a puddle. An ocean of liquid salt water, with more water in it than every ocean and lake and river on Earth combined. About twice the volume. Sloshing around, warmed by tidal friction as Jupiter pulls and squeezes the moon in a slightly off-center orbit. We know it's there because of magnetics. Europa's induced magnetic field only makes sense if there's a conductive layer beneath the crust. Salt water is conductive. Galileo flew past, measured the field, and the answer came back ocean, so the ocean is real. The question is whether we have ever, even once, gotten a sample of it. The Hubble Space Telescope thinks it has. In 2014, Hubble looked at Europa in ultraviolet light and saw bright spots near the South Pole. They looked like water vapor plumes, jetting up from cracks in the ice 200 kilometers tall. In 2016, more. In 2022, more again. If the plumes are real, that means Europa is doing for us what no other moon in the solar system is, bringing samples of its hidden ocean up where a spacecraft could fly through them. Free chemistry, no drilling required. Then somebody went back through Galileo's data. The Galileo probe died in 2003 after years at Jupiter, and its archives had been sitting in storage. In 2018, a team reanalyzed the magnetic field records from a single 1997 flyby. Galileo had passed within 400 kilometers of Europa's south pole, and the magnetic field had wobbled. Not a lot, just enough. The wobble matched what a plume would do. In 1997, the spacecraft probably flew through one, and nobody on Earth knew it for 21 years. Then JWST showed up, the James Webb Space Telescope with its better infrared instruments. In 2023, JWST confirmed something different. Large patches of carbon dioxide ice on Europa's surface. Carbon dioxide that almost certainly came up from the ocean through the ice recently. Geologically recent, within the last million years, maybe much less. So the ocean is real. The vents to the surface are real. The carbon is real. The chemistry is connected to the surface. But here's the part that complicates everything. In 2024, another team went back through 14 years of Hubble's ultraviolet data. They ran the statistics again. They found that the original plume detections weren't as strong as the press releases made them sound. Not artifacts exactly, but not the clean, confirmed jets the headlines had described either. The plumes might be real. They might be sporadic. They might be smaller than we thought. We can't quite tell from here, with the instruments we have. That's why Europa Clipper launched. It left Earth in October of 2024. It arrives in 2030. It will do dozens of close flybys of Europa, and if there are plumes, it will fly through them. It will taste the ocean directly. We will know what's in that water. For the first time, we are sending a spacecraft to a place we already know has an ocean, with chemistry we already know is happening, with a real plan to sample it. 6 years to wait. If anything is alive down there, in a black ocean under 20 kilometers of ice, we are about to know. Number 4. A moon that's eating its own atmosphere. Saturn has a moon called Titan. It is the only world other than Earth where it rains, where rivers flow, where seas pool in the lowlands and clouds drift across the sky. The rain isn't water. The rivers aren't water. The seas aren't water. Titan is so cold, minus 179 Celsius, that the water there is frozen as hard as bedrock. What's liquid on Titan is methane and ethane. It is the only place we know of with a hydrocarbon weather cycle. The methane evaporates from the seas, forms clouds, rains back down, fills the lakes. Everything that water does on Earth, methane and ethane do on Titan, just colder, darker, and slower. So in 2005, two astrobiologists, Chris McKay and Heather Smith, asked a question. If anything is alive on Titan, it probably can't use water. The temperature won't allow it, but it could use methane. Imagine a methane-based life form. Instead of breathing oxygen, it would breathe hydrogen. Instead of exhaling carbon dioxide, it would exhale methane. Instead of burning sugars in a watery cell, it would burn acetylene in a methane cell. McKay and Smith wrote down what that life would do to Titan's atmosphere, if it existed. It would consume hydrogen at the surface. It would consume acetylene at the surface. The amounts would be measurable from orbit. 5 years later, Darrell Strobel at Johns Hopkins ran the actual numbers on Cassini's atmospheric measurements. Hydrogen flows downward through Titan's atmosphere, toward the surface, about 10,000 trillion hydrogen molecules per second, and at the surface, it disappears. Not slowly, not gradually. It hits the ground and it stops. There is no return flow. There is no buildup. Something at Titan's surface is consuming hydrogen as fast as the atmosphere can deliver it. Cassini's spectrometers looked for acetylene on Titan's surface. By the chemistry of the atmosphere, there should be a lot of it. Acetylene rains down. It should pool in the lowlands. Cassini barely found any. So now you've got two missing molecules. Hydrogen disappearing at the surface, acetylene mostly absent from the surface, both predicted almost exactly by a paper that said this is what alien metabolism would look like. McKay himself, when asked, was careful. He said this is possible evidence of life, but it is more likely a non-biological catalyst. A mineral. A surface reaction. Something chemical that eats both molecules without needing a cell to do it. The problem is, nobody has identified that catalyst. 16 years later, the budget is still off. Hydrogen still vanishes. Acetylene is still scarce. The clean chemical explanation has not arrived, and the biological explanation has not been ruled out. In 2028, NASA launches a mission called Dragonfly. It will arrive at Titan in 2034. It is a drone, an actual flying drone with 8 rotors, and it is going to fly around Titan's surface, landing in different places, sampling the ground, sampling the air, looking for prebiotic chemistry, and looking for biosignatures. If there are methanogens on Titan, Dragonfly is going to find them, or it will find the mineral that explains the missing hydrogen. One of those things is true. We just don't know which yet. Number 5, a rock that fell in 1969 that we are still reading like a book. On the morning of September 28, 1969, in the small town of Murchison, Victoria, Australia, a fireball ripped across the sky. It broke apart and rained pieces of rock across about 13 square kilometers of paddock. People watched it happen. They picked the pieces up. Then the scientists arrived. The Murchison meteorite is a carbonaceous chondrite. That means it's one of the oldest, most primitive types of rock in the solar system. It hasn't been melted. It hasn't been processed by a planet. Whatever was in it when it formed is mostly still in it. It is a time capsule from before Earth existed. When the labs ran their first amino acid test in 1971, they expected to find a few amino acids, probably glycine, the simplest. They found 70 amino acids. Most of them were not the ones Earth life uses. Sit with that for a second. Earth uses 20 amino acids. Murchison has at least 70. The other 50 are extraterrestrial chemistry. Molecules that life on this planet rejected, never adopted, never built into proteins. But they exist. They're real. They are made by space, naturally, with no biology involved. In 2017, a team in Japan identified yet another family. 9 new amino acids with an extra oxygen group. Hydroxy amino acids, never before seen in any meteorite, now confirmed in Murchison. In 2019, another team announced ribose, the sugar that makes RNA, in a meteorite that fell 50 years before. In 2010, a German group did the deepest analysis ever attempted on Murchison. They estimated the rock contained more than 14,000 distinct organic molecular species. 14,000 from one rock. To put that in perspective, the entire pharmaceutical industry on Earth has approved fewer than 2,500 small molecule drugs in its entire history. Murchison has more chemistry inside it than every drug ever invented. And it didn't just happen on Murchison. Bennu has the same chemistry. The Japanese asteroid Ryugu has the same chemistry. Other carbonaceous chondrites, Tagish Lake, Allende, Orge, same chemistry. Every primitive rock we look at carefully has this same pantry inside it. This is not a coincidence. The implication is brutal. The molecules required to build life are not Earth's invention. They were not assembled by some special process here. They were already here when Earth formed. They were delivered by every comet, every asteroid, every meteorite that has ever hit this planet. And they're still being delivered right now. Every year, an estimated 40,000 tons of organic material rains down on Earth from space. The chemistry of life is, quietly, falling on your roof. That doesn't prove life is everywhere. It proves the starting line is everywhere. Every planet that ever existed in the right orbit got the same delivery. Every moon that ever sat near a young sun got the same care package. We are not chemically special. We had the same ingredients as everyone else. The only question is whether anyone else cooked. Number 6. A rover baked Martian rocks and found a result that, on Earth, would close the case. In 2012, NASA landed Curiosity in Gale Crater on Mars. Gale is a big, ancient impact basin with a mountain rising out of the middle. The mountain is layered like a stack of books, each layer a chapter of Martian history. Curiosity has been climbing it slowly for over a decade. The rover has an instrument called SAM. Sample analysis at Mars. It is basically a tiny chemistry lab on wheels. It scoops up Martian rock, bakes it to 850 degrees Celsius, and measures every gas that comes off. Curiosity collected 24 samples from across Gale Crater. SAM baked them. The gases came off. The mass spectrometer counted what was inside. And in nearly half of the samples, the carbon was wrong. When you bake organic material on Earth, you get a particular ratio of 2 carbon isotopes, carbon-12 and carbon-13. Most carbon on Earth and in space has a fairly stable ratio between these two. Biology messes with that ratio. Living things prefer carbon-12. It's lighter, it reacts a little faster, and metabolism processes it more efficiently. So when an organism eats carbon and incorporates it into its body, What's left behind is enriched in carbon-12 compared to the source. The chemical fingerprint of life on Earth is a depleted carbon-13 signature, or, same thing, an enriched carbon-12-1. Geologists measure this in a unit called delta carbon-13. -30 to -90 on that scale is the signature of methanogens on Earth, microbes that make methane, the fingerprint of one of the oldest forms of life on this planet. Curiosity measured Martian samples with a delta carbon-13 of -137. Read that number again. -137. More extreme than almost any biological signature ever measured on Earth. More depleted in carbon-13 than coalbed methanogens, and those are the most extreme microbes our biosphere produces. If a geology grad student dropped that sample on a desk in any lab on Earth and didn't say where it came from, the lab would write up the result and say, methanogens. Here is where the video changes. You've been hearing for 5 items now that scientists haven't ruled out life. Bennu hasn't ruled it out. Tabby hasn't ruled it out. Europa, Titan, Murchison, all of them, scientists, in their papers, write the same caution. We cannot rule out a biological explanation, but other explanations are more likely. On Mars, the rover has found the exact isotope ratio that on Earth would close the case, and the team still listed 3 explanations. Cosmic dust falling into the atmosphere and getting buried, ultraviolet light breaking down carbon dioxide in a specific weird way. Methanogens, they wrote them in that order. They preferred the first 2. They could not rule out the third. The only reason this isn't being called the discovery of Martian life right now is that we will not accept the same evidence on Mars that we accept on Earth. That's not a flaw in the science. It's a feature. Science is supposed to be skeptical. When you're claiming the biggest discovery in human history, you need extraordinary evidence. But sit with the framing. We have in our hands a Martian rock measurement that on this planet would be conclusive. We have the spectrum. We have the isotope ratio. We have the geology of the source. We have the depth of the signature. What we don't have is a sample we can bring back and prove came from a cell. Mars sample return is supposed to fix that. It is also delayed, over budget, and currently being rescoped. The samples Perseverance has been collecting and caching on the Martian surface might get back to Earth by 2035. Might. When they get here, we will know. Until then, the answer is sitting in a NASA archive. The data is published. The number is real. And the only reason we are still calling it ambiguous is because the alternative is too big to accept on a Tuesday afternoon. Number 7. A signal that arrives on a clock. In 2007, Duncan Lorimer was going through old archival data from the Parkes radio telescope in Australia. He found a millisecond burst of radio waves that had hit the dish in 2001, 6 years before. He looked at it. It was strange. It was coming from outside our galaxy. It was carrying more energy in 1,000th of a second than the sun puts out in a full day. That 1 millisecond burst is called the Lorimer burst. It was the first known fast radio burst, and nobody knew what made it. In the years since, hundreds more have been detected. CHIME, a radio telescope in British Columbia that looks like 4 enormous half pipes, finds new ones every week. Most of them happen once and never again. Brief, brilliant, gone. Then, in 2012, the Arecibo telescope detected one that repeated. FRB 12102. The same source, over and over. The first repeating fast radio burst. Astronomers traced it to a dwarf galaxy 3 billion light years away. Something out there was firing the same gun, in the same place, on a schedule that wasn't quite predictable. In 2018, CHIME found another repeater, FRB 2018-0916b. They watched it for years. They counted the bursts. And then they noticed the pattern. It clocked in. The bursts come in clusters every 16.35 days, like a season. The source is active for about 4 or 5 days, then silent for 11, then active for 5 again. 16.35 holding steady since 2018. 60 bursts logged from that one source between 2018 and 2021. Same coordinates every time, same period. The source is in a galaxy called M81. 12 million light years away. Not far, by cosmic standards. Right next door. Astronomers want this to be a magnetar. A magnetar is a young, dead star with a magnetic field so strong it would tear you apart from the distance of the moon. We know magnetars can make radio bursts. In April of 2020, one in our own galaxy called SGR 1935 plus 2154 emitted a fast radio burst-like signal. So they can do it. But 16.35 days is not a magnetar period. Magnetars don't have orbital companions. Magnetars don't have seasons. The cleanest model anyone has come up with involves a magnetar with a massive stellar companion, and the radio waves only escape on one side of the orbit. Maybe, possibly, some teams hate this model. The honest truth is that astronomers don't know what is producing this signal. Magnetars can do some of it. Asteroid belts around neutron stars can do some of it. Binary systems can do some of it. None of them do all of it cleanly. So the source is unknown. And the obvious question, is it artificial, is one nobody in mainstream astronomy is willing to print on the record. Because if you say the word artificial in a paper, you might as well kiss your tenure goodbye. But you can ask it here. What kind of natural process makes a millisecond pulse billionths of light years away in a pattern that holds a 16-day clock for years? Nature usually does this kind of thing once, or constantly, or randomly. Nature doesn't usually do active 5 days off 11, active 5 days off 11. Without an orbital explanation, we haven't found an orbital explanation that works cleanly. We haven't found anything that works cleanly. The closest we have is a partial model that some of the field accepts and some of the field rejects. The signal is real. The period is real. The source is real. The explanation is missing. Number 8, life on Earth showed up the moment it could. There's a thing called LUSA, the last universal common ancestor. LUCA is the single organism, the single cell, from which every living thing on Earth descends. You came from LUSA. So did the tree outside. So did the bacteria in your gut. So did the mushroom you stepped on last week. So did the algae in the ocean, and the moss on the rock, and the whale, and the orchid, and the wasp. We've known LUCA had to exist for a long time. What we didn't know was when. In 2024, a team led by Edmund Moody at the University of Bristol published the most careful dating attempt anyone has ever tried. They used 5 sets of duplicated genes that doubled before LUCA existed, so they're shared by every organism alive, and they ran a probabilistic model that combined genetics, geology, paleontology, and clock math. The answer came back. 4.2 billion years. Earth itself is 4.54 billion years old. The surface didn't cool enough for liquid water until somewhere around 4.4 billion years ago. The late heavy bombardment and the period when massive asteroids were still slamming into Earth and sterilizing the surface every few million years was still happening. LUCA was already there. Within 200 million years of Earth being able to hold liquid water, a single cell existed with about 2,500 genes that could metabolize using carbon dioxide and hydrogen, that had a ribosome, that could divide, that could reproduce. That was already part of an ecosystem with other microbes living around it. That is not a slow start. That is the fastest possible start. And here's the thing about Lucy that breaks people. LUCA wasn't the first life on Earth. LUCA was the most recent common ancestor of life that we still have. Whatever came before LUCA, the simpler organisms, the ones LUCA outcompeted, they existed too, and we don't know how much earlier. Abiogenesis itself, the chemistry of dead molecules becoming a living cell, had to happen even before LUCA. So you have less than 200 million years from Earth has water to Earth has a complex working ecosystem with a sophisticated ancestor cell. For comparison, the dinosaurs lasted about 170 million years before the asteroid killed them. The window between Earth could host life and Earth definitely had complex life is roughly the same length as the dinosaur era. That's not a fluke. That's a base rate. If abiogenesis takes only a couple of 100 million years on a wet rocky world with the right chemistry, and we just showed that the right chemistry is delivered by every asteroid that ever forms, then the universe should be lousy with life. Not occasionally, routinely. This is the Fermi paradox in its sharpest form, because if life is fast and easy and the ingredients are everywhere, you need an explanation for the silence. Either the silence is real and something is killing civilizations before they reach the stars, the great filter. Or the silence is fake and we're not listening hard enough or in the right frequencies or for long enough. Either answer is uncomfortable. Luca tells us life was here the moment it could be. Bennu and Murchison tell us the building blocks were already prepared. Europa and Titan tell us the habitats are still available. Tabby's star and the fast radio bursts tell us the sky has unexplained signals. Curiosity's carbon tells us the nearest other planet may already have an answer. 8 quiet discoveries. None of them is the saucer on the lawn. None of them is the message in the sky. They're all chemistry, statistics, spectra, carbon isotopes, and missing hydrogen and ribose in a rock. But they all point the same way. Either life is easy and everywhere, in which case we're not looking hard enough or we're being kept from finding it, or life is easy and everywhere except in one specific place. And you're standing on it. Pick the one that lets you sleep.